Poultry farming faces increasingly complex challenges that demand more than traditional approaches. The cost of poultry products has doubled over the last 5 years due to rising production costs, making it crucial to understand the intricate effects of environmental and husbandry factors on disease outbreaks and feed efficiency. For decades, farmers have relied on correlation-based methods, noticing patterns such as higher temperatures coinciding with reduced egg production. But correlation doesn't tell us why these patterns occur or what will happen when we intervene. This is where causal inference becomes essential. By understanding true cause and effect relationships rather than mere associations, we can make decisions that actually improve outcomes. Today, we'll explore how causal inference combined with digital twin technology is transforming poultry farming from guesswork into precision agriculture. Let's clarify a critical distinction: correlation versus causation. In poultry farming, we might observe that farms using a particular feed brand have healthier birds. But does that feed cause better health? Or do farms that can afford premium feed also invest in better ventilation, veterinary care, and management practices? This is correlation without proven causation. True causation means that changing one variable directly produces a change in another, independent of other factors. For example, if we control for all other variables and find that increasing ventilation rates directly reduces ammonia levels and improves respiratory health, we've identified causation. Understanding this difference is crucial because acting on false correlations wastes resources and may even harm your flock. Causal inference gives us the tools to separate genuine cause and effect from coincidental patterns. Let's dive into some causal questions the farmer might want answered. During a hot spell, is it smarter to lower the house temperature or run the fans harder? Those early morning ammonia smells, are they from poor nighttime airflow or wet litter? Would adding a little extra protein help this week, or is room temperature the real issue? Should we shift the dark hours to calm the flock, or keep the lighting as is? If water intake dips midweek, is it a line problem or just heat stress? And if we change temperature by half a degree, what happens to growth, health, and cost right now? We maintain an operational digital twin of the farm, a structured model of houses, zones, bird counts, controllers, and telemetry, with standardized units, timestamps, and quality flags. IoT streams are cleaned and validated so the data twin provides consistent, high-signal inputs for analysis across sites. When we integrate causal inference methods into digital twin models, we create an analytical powerhouse. The digital twin provides the experimental environment, while causal inference provides the analytical rigor to understand why outcomes occur. Traditional simulations might show that intervention X leads to outcome Y, but causal inference reveals the mechanism. It identifies which pathways matter, which variables are merely correlated, and which interventions will work under different conditions. For example, the system might discover that improved ventilation reduces mortality not directly, but by lowering ammonia levels, which reduces respiratory stress, which decreases disease susceptibility. Understanding these causal chains allows you to optimize interventions more precisely. You might find that moderate ventilation increases combined with air filtration achieve the same health benefits as maximum ventilation alone, but with lower energy costs. This integration transforms the digital twin from a prediction tool into a true understanding engine. Our approach combines fast causal inference and expert domain knowledge with farmers to co-design DAGs, then uses due calculus to determine which causes are identifiable. These rich causal DAGs become part of our IP. Once a cause is identifiable, we train meta-learners on the farm's high-resolution telemetry, specifically double machine learning models via DOY and EconML from Microsoft, to estimate conditional treatment effects. Because Causal ML lacks direct labels, we safeguard estimates with a robust uncertainty suite that separates aleatoric, irreducible noise from epistemic, lack of knowledge overlap, and we run sensitivity analyses, e.g. Rosenbaum bounds. We act only when CIs are narrow, epistemic uncertainty is low, and sensitivity indicates robustness. Otherwise, we flag a non-actionable treatment and propose a small trial. Today, most solutions focus on monitoring, anomaly detection, and forecasting. Causal effect estimation in poultry is new, but the timing is right. Farms now run dense sensor networks including temperature, carbon dioxide, ammonia, intake, weight, and more, so key confounders are observed more often. Poultry houses are closed-loop, highly controlled systems, making identifiability more attainable. That's why we believe Causal ML can finally move from theory to reliable interventions on real farms. We have already engaged multiple rural smallholder farms and sensor vendors, confirming that environmental monitoring is still currently minimal or absent in these operations. To close this gap and to enable causal inference for small farmers, we are developing an affordable and low-maintenance sensor kit with our partner LNX, purpose-built for small broiler houses. These systems will be deployed for free in our first round of select pilot farms to validate the platform, collect high-integrity data, and uncover key causal drivers of welfare and performance. The insights and results from these pilots will be published as case studies and used to scale adoption through cooperatives and funding partners, ensuring responsible, inclusive growth from the start. Welcome to OptiBroiler, where we optimize broiler farm performance using advanced artificial intelligence. With our solution, you can learn more about our system, explore a guided demo, or go straight to the interactive dashboard to experience how it works in practice. Our dashboard is directly connected to a virtual farm that we have developed. This virtual environment captures all the data and dynamics you might find on a real farm. It allows us to set clear data standards and interfaces, showcase our solution, and continuously refine our AI models and assumptions for identifiability. The front page of the dashboard provides an overview of the farm's current state. Here you can monitor the overall health of your flock, track daily profit, review the poultry efficiency factor, and analyze feed conversion ratios. The system also highlights any critical alerts, such as ammonia spikes in specific houses, and provides an at-a-glance overview of all poultry houses. In addition, reports can be generated to compare farm performance when recommendations are followed versus when they are not. While each recommendation may seem incremental on its own, their cumulative effect across a 6-week growth cycle and over the course of a year drives substantial profit gains. The operations page offers deeper insights into anomalies and risk factors within individual houses. For example, it can highlight dust concentrations that may harm respiratory health, sharp increases in ammonia levels, or reduced chicken activity. This page consolidates a broad range of key metrics, including bird weight, temperature, efficiency factor, daily mortality, and feed conversion ratio. Environmental indicators such as humidity, carbon dioxide, dust, and ammonia levels are continuously monitored, along with chicken noise as a potential stress indicator, airspeed for ventilation, and movement indices to assess bird activity. Additional parameters such as spread uniformity, feed intake progression, and power consumption are also tracked, ensuring both flock welfare and farm profitability are balanced. At the heart of our platform is the AI Advisor, which delivers weekly data-driven recommendations throughout the 6-week production cycle. Across the 6-week cycle, we train house-specific DML learners for each week, estimating effects for available treatment levers on the poultry efficiency factor, PF. These recommendations are grounded in causal inference models that identify which interventions have the greatest measurable impact. In early weeks, the system may recommend controlled experiments to generate stronger data support, helping improve the precision of future advice. Currently, recommendations focus on single treatment adjustments, for example, a slight increase in protein levels, which can lead to a measurable uplift in poultry efficiency factor and improved profitability. Each recommendation comes with our uncertainty measure, based on our causal uncertainty and sensitivity measures, indicating the level of confidence and data sufficiency behind the causal inference. The advisor also provides dosage response curves, showing how changes in parameters such as protein, temperature, ventilation, or lighting affect outcomes. These curves highlight optimal ranges while clearly marking danger zones, where insufficient data prevents reliable conclusions. While the system's strongest support is for single treatments, it also offers multi-treatment scenarios, such as adjusting both protein levels and temperature, allowing farmers to explore the most effective strategies while understanding the associated risks. In conclusion, OptiBroiler combines real-time monitoring, predictive modeling, and AI-driven advisory tools to deliver a powerful solution for poultry farming. By enhancing operational efficiency, effective digital twins depend on comprehensive, accurate data collection. Modern poultry farms deploy networks of sensors throughout facilities. Temperature and humidity sensors at multiple locations capture microclimates within barns. Air quality monitors measure ammonia, carbon dioxide, and particulate levels. Automated scales track individual or group weights, revealing growth patterns and potential health issues. Camera systems with computer vision analyze bird behavior, detecting signs of stress or illness before they become obvious. Feed and water consumption sensors provide precise intake data. All these devices communicate wirelessly, transmitting data to central processing systems in real time. The infrastructure is designed for reliability, with redundancy to prevent data loss. Regular calibration ensures accuracy. This continuous monitoring creates a detailed, moment-by-moment picture of farm conditions, enabling the digital twin to maintain fidelity with physical reality and provide insights that would be impossible through manual observation alone. Responsible innovation is at the heart of what we do. Using AI in agriculture means protecting animal welfare, empowering farmers, and strengthening food security. We have already engaged multiple rural smallholder farms and sensor vendors, confirming that environmental monitoring is currently minimal or absent in these operations. To close this gap, we are developing an affordable, low-maintenance sensor kit with our IoT partner LNX, purpose-built for small broiler houses. These systems will be deployed in pilot farms to validate the platform, collect high-integrity data, and uncover key causal drivers of welfare and performance. Validation will be conducted collaboratively with farmers, veterinarians, and local experts through field trials and real-world benchmarking, ensuring that the technology performs reliably under diverse conditions before wider adoption. The insights and results from these pilots will be published as case studies and shared through cooperatives and funding partners, supporting transparent, evidence-based scaling. To enable equitable adoption, we are developing easy-to-access onboarding guides, hands-on manuals, and multilingual support channels tailored to farm workers and technicians of varying educational backgrounds. Possible workshops and digital literacy training will help bridge complexity gaps and build confidence in using the system effectively. Farmers will remain the owners of their operational data. By granting secure, licensed access, they enable the generation of anonymized, aggregated insights across the network, continuously improving recommendations and ensuring that every participant benefits from shared knowledge. Accountability and transparency are built in. Farmers and veterinarians remain the final decision makers, supported by clear confidence indicators and real-world validation. This is how we scale responsibly, with data that protects welfare, insights that drive profitability, and technology that empowers even the smallest producers to compete and thrive. The future potential of this technology extends far beyond poultry farming. The same principles of causal inference and digital twins can transform dairy operations, swine production, and even crop farming. Integration across agricultural systems could optimize entire food production chains, from feed crops to final products. Global food security stands to benefit enormously as these technologies help farmers worldwide produce more efficiently with fewer resources. However, scaling presents real challenges. Infrastructure requirements, particularly in developing regions, are substantial. Farmers need training not just in using the technology, but in understanding the principles behind it. Economic barriers must be addressed through innovative financing and cooperative models. Cultural adaptation is necessary, as farming practices vary globally. Despite these challenges, the trajectory is clear. Agriculture is entering an era where data-driven, causally informed decision-making becomes standard practice, enabling us to feed a growing population sustainably. Our team brings together a multidisciplinary mix of skills spanning AI, veterinary science, engineering, and design. Dylan, our machine learning engineer, leads the causal inference and uncertainty estimation pipeline, ensuring our models are both rigorous and explainable. Ryan, a practicing veterinarian with direct farm experience, keeps animal welfare and operational feasibility at the heart of our system. Taliya, a biomedical and electrical engineer, connects the hardware and software layers, from sensors and data pipelines to applied AI. Heinrich, a physics-trained ML PhD student, supports model validation and the construction of our virtual broiler environment. Corey, our application engineer, builds scalable dashboards and ensures the interface is intuitive for farmers and technicians alike. We also collaborate closely with partners on farmer onboarding and feedback integration, ensuring the technology is rooted in real agricultural practice rather than abstract theory. Together, we embody the deep learning Indaba's mission, strengthening African AI through research that is both technically ambitious and socially grounded. By applying causal machine learning to food security, one of Africa's most urgent challenges, we show how advanced AI can deliver tangible impact, build local capacity, and empower communities. In essence, this is African AI for African agriculture. Technology that learns from the continent, serves its people, and safeguards its animals. Technology alone won't transform agriculture. Responsible innovation will. Our platform combines causal AI with farmer expertise to improve welfare, performance, and sustainability together. We design with veterinarians and farmers to ensure transparency, accountability, and real-world usability. The future of agriculture isn't about replacing people. It's about empowering them with better insight, so farms become more productive, more competitive, and more humane.